This is the acid-base equilibrium, and this is where the fun begins, and by fun I mean calculations of weak gas systems. Okay, so here we go. If we look at our acids and our bases, they are really simple K expressions. But in this case, the only thing that does drop out is water will drop out in the base, but other than that, it's the products, remember, over the reactants, so the weak systems, etc. Now the Ka and Kb values are on a chart, and you can use those for my problems most of the time, and they can change about every couple of years. I update them, so a lot of times I'll just go ahead and give you the Ka I used on a problem. So for example, in the extra acid base problems, you may be given a Ka, and it may vary slightly. That's because they're constantly updating them. Okay, these are weak acid base problems. They are strictly equilibrium problems. So you're going to set up an ICE table. You'll use the polyatomic function in your calculator. That's the polyfunction, the quadratic, the solver, whichever one it is. The advantage to the weak acids and the weak bases, unlike the KSPs or any of the other ones, is you're only going to lose or gain one proton at a time. So as we work problems, it's only one proton. And they're all interrelated in terms of, we talked about the H plus, the OH minus, how they're related to KW. Same thing with Ka and Kb. So it's kind of a circular revolving door. Once you get one, you've got the other three. Now, the tricky part is we're back to the concept of who's got the proton. If it's acidic, you must have H plus, but if it's basic, you must have OH minus. And if you have OH minus, you're not going to have H plus, and vice versa. So these are simple problems to work. They're kind of fun, other than the whole foil thing. But we've got to get started with the ionization equation and the ionization constant. So first off, let's look at HF. HF is a weak acid, so it's H plus F minus. So the Ka associated with it is F minus times H plus divided by, HF. Okay, so B is actually starting with a conjugate. It's a base, so we're going to have to put in water. So we'll end up with HCN plus OH minus. So this is actually a Kb. When in doubt, look at it, Cn minus. There's no proton, so it can't be an acid. So in this case, the protonated form of the acid in the hydroxide appears on the numerator. In the denominator, we have cyanide minus. Okay? So on C, this one is C6H5NH2. Based upon what we know about nitrogen, there's no oxygen present, so odds are it's basic. So we would pick up a proton, so C6H5NH3 plus OH minus, because we picked it up from water. So again, this is a Kb, so it's C6H5NH3 plus times OH minus over C6H5NH2. So if you look at these are really simple equilibrium. The beauty of them is they're one at a time. So you're only gaining or losing one proton, which makes these easy math-wise, other than you get to foil them. Okay, so what is the Ka of butyric acid, a weak organic acid, if we're given, etc. So I'm going to call this H-but, okay, because I don't want to write all that. You can call it Fred for all I care, but just make sure I know what you're calling it. So we're going to start with H-but. Is going to dissociate. It's a weak acid. We know it's a weak acid for two reasons. The main one is well, about three reasons. We're given the Ka, we're given butyric acid, and if you remember, that's the carboxylic acid. So we're going to end up with but minus. Okay, so this is a simple equilibrium. It's an ICE. If we start off with initially of 0.25 molar here, and this is 0 and this is 0, So we're moving one proton at a time. So we're going to gain where there's a 0. So we have 2.25 minus x, and x here. So if we were looking over here, our K expression, which is a Ka, would be H plus times but minus divided by H but. Now, right now, all I'm doing is setting up all my information. Okay, so wait a minute. We're asking for the Ka, so this is what we need to know, which means we have to know the values there. We're given one other piece of information. That means our pH is 3.21. Now, I walked you through the fact that the hydronium ion concentration is going to be 10 to the negative pH. That means it's 10 to the negative 3.21. When we run that through, we're going to get a value of 6. The H plus concentration is going to be 6.16595 times 10 to the negative 4th molar. All right, so that means that that is the X value. So it'll go in here, here, and here. So we end up with 6.16595 times 10 to the 4th, negative 4th. So since it's in there twice, we'll just go ahead and multiply by 2. And then we'll subtract it. So 0.25 minus that value gives us 0.2493834. And once we run this, this is the Ka, which is what we're looking for. So your Ka value, once you run it, is 1.5245 times 10 to the minus 6th. Again, Kas have no units. You have to use molarity going in. Typically going to keep 4 significant figures. So that's 1.525 times 10 to the minus 6 is equal to your Ka value. So this one was relatively easy, straightforward. It does involve a number of steps associated with it, but we'll do another one. Okay, one other thing I want to look at is percent ionization. So this is real simple. This is whatever the conjugate is. So it's the product, acid form, base form, whatever, over the fully protonated. And this is the, or the reactant. Now, this is called the formal concentration. Okay, same as the original initial before any dissociation. So, for example, if we were looking back here, the formal concentration, okay, let me not put it here, H-but. So the formal concentration of H-but from before was 0.25. We do not take into account any dissociation, etc. So that's what the formal, so that's assuming that nothing happened. So even if you've calculated that value, you're not going to use it. All right, so how do we use it? We'll move on to it here. What is the pH of a 0.1 molar of hydrozoic acid, etc.? Okay, well, if it's hydrozoic acid, we have to have a Ka. So it's 1.9 times 10 to the minus 5th is the value we're going to use. And so we're asking for the pH, and then we're going to do the percent ionization. Okay, so hydrogen azide is going to dissociate into H plus the azide minus, it's an equilibrium, so we have an ICE table. So initially we're going to start with 0.15 molar, and we have nothing dissociated. Remember, if you don't put it in, you don't have it. So you're going to lose that here, you're going to gain here, so your equilibrium value is 0.015 minus x, and x. So my Ka value is going to be H plus times azide over azoic acid, hydrozoic acid. So we end up with x times x divided by 0.015 minus x is equal to 1.9 times 10 to the minus fifth. Now, this is where we start multiplying. So we end up with x squared is equal to 1.9 times 10 to the minus fifth multiplied by 0.015 minus x. So when we multiply it out, we get x squared is equal to 2.85 times 10 to the minus seventh minus 1.9 times 10 to the minus fifth x. So when we put them all together, x squared plus 1.9 times 10 to the minus fifth x minus 2.85 times 10 to the minus seventh is equal to 0. Now, in this particular case, we didn't need to FOIL anything. However, we still do need to use the quadratic because now we've generated a quadratic expression. So I'm going to move up here. So when I solve for x, I'll get two values. We're only going to keep the one that is good. Remember, it's the one that's not negative and the one that is less than the values. So that's what x is molarity wise, which means that x is the same thing as H plus, which is the same thing as the azide. And the HN3 concentration is going to be 0.015 minus the x. So that means the H plus is equal to the azide is equal to 5.24438 times 10 to the minus fourth. Now remember, you don't have to rewrite all of this stuff. I'm just walking it through so that there's less confusion. And so if we were asked the concentration of the azide, we could find it, which we're not actually asked for it, but I'll go ahead and do the math. 0.015 minus 5.24438 e to the minus 4. So you end up with 0.014476. Okay, so wait, what was the question? The question was we want the pH, which is equal to the negative log of the hydronium ion concentration, which is equal to the negative log of 5.24438 times 10 to the minus fourth molar. That means my pH, and remember we're keeping the pH two places after the decimal. That's my pH. That's the first question. Then the other one is the percent ionization. And that's going to be the azide divided by the formal concentration of the hydrozoic acid times 100, which means it's going to be 5.24438 times 10 to the minus fourth divided by 0.015 molar times 100. Now somebody's going to say, wait, we subtracted it. Did we have less? Yes, we do now. But when you're doing percent ionization, you use the formal concentration as if there's nothing lost. So we end up with a whopping 3.4963%, which if we're keeping 4 decimal places, that's 3.496% ionization. Now, rule of thumb says it's less than 5%. So we could have made an assumption that it was minimal and be okay. But since we're in the age of high tech and calculators, you can run it. All right. If a 0.1 molar solution of picric acid has an 82% ionization, calculate the Ka of the acid. Okay. Well, I'm going to call this acid H-pic. So if we have H-pic, it's going to dissociate into H plus pic minus. We have an ICE. We're going to start with 0.100 of that minus X plus X plus X, 0.1 minus X, X, and X. Okay? Now, We know that the Ka is going to be equal to H plus pic minus over H pic times 100. No, that was wrong. Okay, I'm confusing my rules. Okay, we know that. So the problem is this is our unknown, and right now we have X. So are we given another piece of information? Yes, we're told that we have an 82% ionization. So that means that the 82% is going to be equal to the pic minus divided by H pic times 100, and this is our X, and this is our 0.10. So that means that our pic minus is going to be equal to 0.82 times 0.10 molar, which gives us a value for X of 0.082 molar. So this is X. So that means we have this value, which is 0.082 squared. And now we need the H pic value. So the H pic value is going to be equal to 0.1 minus 0.082, which is equal to 0.018 molar. So this is 0.018 molar. Now, at this point in time, I'm looking for a Ka value that's pretty large. So this is still a weak acid, but it's a strong weak acid. And I know that because it's 82% ionized. Remember, you're thinking about ionization. Strong acids and strong bases are 100% ionized. 82 is pretty close. So of the acids, this is actually a strong weak acid. So my Ka is equal to 0.3736. And if you wanted to write it in scientific notation, you don't have to, times 10 to the minus 1. Okay, so this means that it's pretty close to 1, which means this is a really strong weak acid. Okay, picric acid is kind of interesting because it's shock sensitive if it gets dry. If it's wet, you can play football with it. You can drop kick it wherever you want, put it in a soccer ball. Sucker dries out, you touch it, and it can go boom. Which kind of makes it interesting. Alright, a weak acid has a Ka and a concentration of 0.1 molar. Calculate the pH and the percent ionization. I don't know what the weak acid is, so we're just going to go with our generic weak acid. A minus. So again, it's an ICE table. Our Ka value is given. We have an initial concentration of 10. So this is 0, 0, minus X, plus X, plus X. 0.1 minus X, X, and X. That means my Ka value is going to be equal to X squared divided by 0.1 minus X. And we know our Ka value is 1.7 times 10 to the minus 10th. So we do our math and we get X squared plus 1.7 times 10 to the minus 10th X minus 1.7 times 10 to the minus 11th is equal to 0. So all I did here was my algebra. Now I'm going to put it through the poly function. And I find out that X is equal to 4.12300206 times 10 to the minus 6th molar. Now remember, this means that's our H plus and our A minus. Now, we wanted the pH, so the pH will be the negative log of the hydronium ion concentration, which is 4.123 times 10 to the minus 6th, which means my pH is equal to 5.38. So while it is acidic, it's pretty close to neutral. Our percent ionization is going to be equal to the A minus times the HA, formal, times 100, which means it's going to be 4.123 times 10 to the minus 6th divided by 0.1. Remember, we need formal, which means there's no dissociation. So our percent ionization is a whopping 0.004123. So looking at this one versus the 82% on the previous, this one's tiny. So what's that tell you? That this is actually a pretty weak acid. And if you look at times 10 to the minus 10, that's a really weak acid. So this is a really weak acid, unlike the picric acid, which was a really strong weak acid. All right, so we've done weak acids. Now let's do weak bases. Now weak bases have one extra step. You're going to solve for the OH minus concentration, which means you're going to end up with the POH, which means you have to do 14 minus the POH to get the pH. That is the only thing, is there is an extra step there. Okay, so calculate the hydroxide ion concentration of the pH of the solution of cyclohexylamine. Okay, I really don't want to write that formula, so I'm going to call it CHA, cyclohexylamine. Ha. So we're going to start with our CHA, and it's a base. So with bases, you have to add in water because you have to have a source of the proton. So we end up with CHA plus, HCHA plus OH minus. It's a simple ICE. We have 0.015 here, 0 and 0, minus X plus X plus X. So it's 0.015 minus X, X, and X. So your KB is, oh wait, we needed a KB. So I'll go look that up on the chart. I find out the KB is 4.6 times 10 to the minus 4th for the cyclohexylamine. Okay, so it's going to be X squared divided by 0.015 minus X is equal to 4.6 times 10 to the minus 4th. We will distribute and get X squared plus 4.6 times 10 to the minus 4th X minus 6.9 times 10 to the minus 6 is equal to 0. So we solve for X. X is equal to 0.0024068, which is equal to the HCHA conjugate and the hydroxide. So we're asked for the OH minus concentration. So we'll take the POH, which is the negative log of the OH minus concentration, 24068. And so my my POH comes out equal to 2.62. Subtract it from 14, so you get your pH is 11.38. All right, just out of sheer meanness, I didn't do this, but if we were asked for percent ionization, it would be 0.002468 divided by 0.015 times 100, which, let's go ahead and do our math. 0.002468 divided by 0.015 times 100. So this actually has a pretty good percentage. If I did it right, I got 16.0453%. So for significant figures, it'd be 0.05% for the percentage. Now, that actually makes sense if you look at your KB. Your KB is about the minus 4th range. As the K value gets smaller, -4, -3, -2, -1 versus -10, -9, etc., then your percent ionization will increase because that means it is a stronger weak acid. All right, so we're going to calculate the pH and the percent ionization of ammonia. Now, most people should recognize immediately that this is a base. And if you look it up, you'll find it on the KB section. And there's the KB. So here's ammonia. Again, you'd have to add water. That's one extra step. NH4 plus, you get ammonium ion plus hydroxide ion. So it's an ICE, so 0.25. 0 minus X plus X plus X. I don't know what that screwy thing was. 0.25 minus X, X, and X. So in this particular case, your KB expression is x squared divided by 0.25. Typos, because the numbers are really small, are easy, so be careful. Times 10 to the minus fifth. We distribute, we get x squared plus 1.8 times 10 to the minus fifth x minus 4.5 times 10 to the minus 6. Now, somebody may have figured out, wait, we have 4.5. That's not four significant figures. It actually is, because when you multiply 0.25 by 1.8, you get that value. So your x value comes out equal to 0.002112, which is the ammonium ion and the hydroxide ion concentrations. So if we wanted the pH, then we're going to have to do 14 minus the POH. So the POH is going to be negative log of 0.002112, which gives us a whopping 2.68. And remember, that's the POH, so the pH you subtract is equal to 11.32. So this is actually a pretty basic solution. You're asked for the percent ionization, which again will be the conjugate, which is 0.002112, because that is the ammonium ion, divided by the formal concentration, which is the ammonia, times 100, which gives you a whopping 0.8449%. So this is actually, that seems a little small. I'm going to double check it. 0.02112 divided by 0.25. Nope, that's right. Actually, I got 0.84408. But other than that, it's right. No, it's not. Yes, it is. Can't read. So life is good. So you just have to follow your numbers. Sometimes the numbers look weird and sometimes they don't. This is actually kind of weak acid, weak base. So therefore, it's still pretty basic when you're done. But you have to think about these species, etc. So this is the calculations. Now, if you noticed, I did weak acids and then I went and did weak bases. The textbook tends to do all of your acid stuff and then they do your base stuff. To me, that's ridiculous, because that implies that they're different. They're really not. The bases have an extra step where you convert the POH to the H. But other than that, they work identically. They're just simple Kas, or bases, or KBs. So we're good to go there. Now we're going to take it up a notch and move to salts.